Now I would like to welcome Dr. Anil Kumar again. This time he will be presenting about fluid structure interactions. Welcome back, sir.
Thank you.
Yeah.
Shall I start?
Yes, sir. Go ahead.
Welcome back, everyone. This session is on fluid structure interactions, which is an evolving field and where a lot of research and consolidation of different methods are being done now. First, we will see an introduction and look at different scenarios involving fluid structure interactions, different types of interactions, and appropriate methods for them. This involves a stationary rigid structure and fluid flow, or moving rigid structure and fluid flow, or deforming structure and fluid flow, including structural failure and geometry changes, structural changes which may change the flow boundaries themselves. Finally, we will look at one or two problems involving flow through and the deformation of porous structures. If you look at multi-physics in general and fluid structure, the engineering problems involve more than one physical or chemical processes. But normally we simplify them, isolate them and simplify them for the sake of ease of solving these problems. But nowadays, with the development of techniques and coupling of the techniques, it is possible to study the process in a coupled manner. For example, a problem may involve solid mechanics or fluid mechanics, heat transfer in all the structures and fluids, and with the surface reactions, or it could even be coupling between electromagnetics and the flow and structure and so on. For example, take how a parachute works. It is closed in the beginning, and as it opens, you can see that it displaces the air, and also the air exerts more resistance to the fall of the parachute. So you can see that the opening of a parachute and its descent involves the deformation of the fabric as well as the ties and the ropes attached to that. And at the same time, it affects the fluid flow, air flow around it. So there is a two-way coupling between these problems. So this problem cannot be solved in isolation. It may have to be solved in a coupled manner. When we study this problem, we have to consider both the structural deformation and also the fluid flow around it. So there are different levels of the fluid structure interactions. So first, the simplest one we can say in terms of fluid structure interaction, it's the effect of stationary structure on the fluid flow. So when you have already solved various problems involving this, in this case, the flow domain remains the same. So, and actually, when we look at the fluid flow problem, we solve the flow field or the flow variables in a domain bounded by solid or structural walls. So essentially, all the problems are fluid structure interaction problems. So in this case, let me introduce one method which is called immersed boundary method, which is gaining popularity due to various reasons currently. So if you look at this problem of a flow around a cylinder, this problem can be solved in a conventional manner by generating mesh inside the flow domain and having a surface where the cylinder is modeled as a surface, which you already may be familiar. So we get the flow around it. This surface of the cylinder is treated as a boundary surface, and wall boundary conditions are applied here. That is how it is normally done. But just to demonstrate the immersed boundary method, in the immersed boundary method, we don't need to generate a mesh which is fitting the surface of the cylinder. We can have a Cartesian mesh like this, and then there can be a separate surface mesh, surface representation of the cylinder, and we can tell the solver that there is another surface at this location. Then the fluid flow solver is modified to include the presence of that surface. For example, I have shown the basic equation. This is a momentum equation. That is, rate of change of momentum is equal plus the convection equal to the pressure gradient and the viscous stresses, buoyancy force. And there is another term, a source term. This source term takes into account, or it is to consider the effect of the wall of this body. So this is immersed boundary method. You see the result here. The first picture shows the velocity profiles obtained. You can see that the flow comes here, the uniform flow in this direction from left to right. Then there is a stagnation point in front of the cylinder. You can see the pressure conduce. There is a stagnation point. And there is no flow inside that cylinder because that immersed boundary method takes care of that. You can see the wake of the cylinder. There is a magnified picture of the velocity vectors here. There is another method to treat the fixed rigid structure, which is simpler than or easier than conventional mesh generation methods, which you already might have heard about in yesterday combustion simulations. These are called a subgrid methods, where the same problem, we say that there is some region, we set the porosity, that is, the porosity is the volume available for fluid to occur, or to exist. So in a structure, there is no fluid, there is no volume for the fluid. So porosity of a solid structure is 0. So if we can model by just specifying this porosity, 0 porosity to the region represented by the structure. May not be accurately, because if you use a Cartesian mesh, you will not be able to represent a cylinder or a complex shape accurately. But for many practical problems, it is sufficient to define an approximate region. There are different levels of approximations. So if we use this extensively in large scale problems with complex geometries and involving complex problems. For example, explosion in a closed domain with multiple obstacles. It may not be feasible to model all the objects very accurately. For example, if you take a refinery, for example, there could be large number of pipes and small pipes. Or even in a normal room, for example, we have a lot of small things, bottles or tables, chairs, and so on. And it is very difficult to represent them accurately. And at the same time, from the analysis, we may not require very accurate result. What we may be looking for is maybe 10% or 90% accurate result. In that case, we can represent these objects using porosity or subgrid scale models. So this is one example. You can see that the results, we have shown the overpressure from explosion are compared with experimental data. With these models, we can get the reasonably accurate result with less computational time and memory. So, for example, in this case, this problem involves a possible explosion of hydrogen in a retail outlet. As all of us know, people are talking about hydrogen economy, and there is going to be hydrogen outlets. So hydrogen is a highly reactive mixture. So in case of a leak, it could, of course, it will go up due to buoyancy effects, but still there could be in an enclosed, partially enclosed domain, the possibility of hydrogen getting accumulated and getting exploded. So a lot of studies are being done whenever you set up, whenever such outlets are set up, to make sure that in case of an accident, the explosion doesn't happen, and if at all explosion happens, the pressures are lower than the safe limits and so on, or to install sufficient safety measures. So in this case, you can see that there could be a vehicle in the outlet, and then there could be other objects representing, etc. In all these cases, we can we have used this kind of method, and can see that comparison. There are some benchmark problems and test results. So all the software is offering such solutions should go through this kind of validation process. We can see that the pressure variation with the time, the simulated values are reasonably well matching with the experimental data for various conditions. So now the second type of fluid structure interaction is where the so what we have considered is the effect of a stationary structure. Now in this case, the structure may be moving, but with a prescribed motion. So it is like a one-way coupling. The structure is moving, but its movement is not determined by the fluid flow, but it is prescribed or it is forced by some other means. For example, a movement of a piston. So the resistance offered by the fluid may be very small, insignificant compared to the external force. So we can ignore the effect of the fluid on the piston. There are various methods to model this kind of problems. One is the wall velocity conditions. You might have seen in some of the problems when we set up a problem, we can specify wall velocity. Velocities at the walls. But it is sufficient in some of the cases. And then there are inertial and non-inertial reference frames, then rotating frame of reference, and so on. But here also, we can use the immersed boundary method. The short form is called, it's also called IBM. For example, you take the lid-driven cavity problem, which is a standard problem in computational fluid dynamics. If you want to model a lid-driven cavity problem with the lid moving, normally we take this domain and create a mesh corresponding to the lid and apply a wall velocity at the lid. But instead, we can solve this problem using the immersed boundary method. So, for example, you take this mesh here, and the lid is modeled like this. That is, mesh for the surface is created like this. You can see that, and velocity is applied. So you can see that the normal mesh, it's very simple. It doesn't have to be inclined. It's like a normal Cartesian mesh, but we can put a sloping surface there. You can see the velocity profile here. The lid is moving in this direction, so it induces the correct recirculation in the domain. Or if in the case of a moving piston problem. So as an example, I have shown what is called Orifice pulse device, which is which is actually used to cool, to take away as a heat exchanger, Orifice pulse tube, OPT. It operates like this. There is a piston here, and then there is an orifice and a reservoir. And as the piston moves to the right, it forces the fluid to pass through a small orifice, which as it expands, it cools down, and that heat is taken out the reservoir. And on the way back, there is a reverse flow. So we want to model this problem. For example, at the end, there is a oscillating piston, and the air in this region gets compressed in this region. And there is a small orifice here. It expands. This is the reservoir. So here you can see we are showing the velocity, the speed along the axis. So as the piston moves from left to right, first the fluid, the gas goes into the reservoir. Then as the piston moves back, there is a reverse flow. And at monitoring at different monitor points, we can see there are 5 monitor points. We monitor the pressure and velocity, and they are plotted here at each point. And it can be seen that the phase difference between pressure and velocity is about 90 degrees, which is expected. So this is an example of moving a structure moving at a specified speed. Now, a little bit the next level of little bit more complex problem, where the movement of the rigid structure, it is not prescribed, but it is determined by the fluid flow also, the flow of the surrounding behavior of the surrounding fluid also. So here, as the structure moves, the structure is still rigid, it doesn't deform, but as it moves through the flow field, it changes the flow field. Maybe it increases the pressure of the fluid. Then that increased pressure will exert different force on the structure. So this is a two-way coupling. The fluid, the structural movement affects the fluid flow field, and the affected flow field affects. Again, for this kind of problem, there is another example where we have used immersed boundary method. So you can see that immersed boundary method is a versatile method, properly used. It can be used to study very complex problems. So this problem involves the movement of a valve. This is a water tank. There is a valve which is connected to a hinge. So the gravity is acting downwards. So the valve, the free fall of the valve, it may fall like this. But it is hinged here, so it will rotate and then oscillate and come to a steady problem. So its movement, movement of such structures through the water, it affects the performance of the behavior of such heavy valves. These are very heavy metallic valves. So the angular acceleration of the disc, which is hinged at this, and it depends on gravity. That is one force acting in the downward direction. And also, when it is coming down, it is resisted by the forces exerted by the fluid. So the net for the total force is a sum of these two forces. So we show a mesh generated. So you can see that the fluid mesh, that is that the discretization of the tank, water tank, is a very simple mesh. It's a Cartesian mesh, the structure, and you can see that the fluid mesh does not conform to the valve. It is made without considering the valve. Then later, a surface mesh is generated for the valve independently, and they are integrated. For example, in fluid and GUI, you can load multiple meshes. You can load a fluid mesh, and you can load a structural mesh, which is created separately. And the software automatically identifies their overlapping regions. So here, you can see the result here. So at any point, the fluid mesh does not move. So this structural element or this the wall, it moves through the fluid element, cutting, making intersection. But the immersed boundary method or the condition applies there. We can see that it generates the correct flow pattern. As the wall moves down, it pushes the flow, it pushes the fluid in front of it, and it drags the fluid behind it along with it. And as it falls, in the first cycle, it comes to the horizontal vertical position, and it crosses that because of inertia. But it comes back again, and it loses its energy through viscous its dissipation to the fluid, and finally comes to rest. And this graph here, angle versus time, shows the comparison of simulation results with the experimental data. So I show again the modeling of the two-way coupling problem. This is a problem involving a torpedo launch from a submarine hull. As you know, the submarines, they launch torpedoes. There are, if you look at the hull of a submarine, there is a small cylindrical cavity in the surface, and torpedoes are kept inside them. And initially, there are different mechanisms of launching the torpedo. One of them is that there is a spring kind of thing attached to the back of the torpedo, to the submarine structure. And as you can see, when it is launched, that spring push, you can see a narrow red color line in the left side, and it pushes and it accelerates the torpedo to certain speed. And after that, the torpedo gets its own things, and it goes out of the domain. So that yellow color region is the water, sea water, and the red color is region is the torpedo. So you can see that as it moves out, there is a low pressure region generated behind the torpedo where there could be cavitations and so on. And it drags the water also. And we can clearly see the stagnation point in front of the torpedo and the wake. You can see that the stagnation point, the red color patch on the nose of the torpedo, and there is a low pressure wake region behind that. So this is done. This is simulated using IBM. The advantage here is that immersed boundary method does not require complex mesh adaptive meshing or such mesh restructuring and so on. But there are certain limitations for that. It is definitely not as accurate as the mesh is fitting the surface of the bodies. But further developments in that area will are making it more and more accurate and efficient. Similarly, you know that the right side shows a shock absorber model for a shock absorber or a two-wheeler shock absorber. The basic principle is same as that of a gun recoil system. So in this case, it was modeled using the same technique, using a moving mesh method. And there is further a very simple way of modeling structures in many cases. For example, just by adding a sink term or a source term in the momentum equation, we can model the movements of solids through fluid. So this problem is called a prover problem. This is a component or a system in the petrochemical industry. So what happens is that it's a sort of valve, it's a spherical valve kind of thing. And there is flow from the bottom. As you can see from here, there is a flow from the bottom. It lifts the this sphere, spherical valve, and it may close this opening here. So here only the fluid mesh is generated, and the sphere is selected, a spherical region is selected, and the porosity of that region is set to 0, and appropriate source terms are added. And you can see that it captures the interfaces and the velocity profiles quite well. So there are methods which can produce the results at different levels. The most accurate is, of course, a correct representation, accurate representation of the surfaces and geometries, but they are also more difficult to generate mesh in many complex movements or complex geometries. But if you are looking for somewhat accurate solution, there are other methods like immersed boundary methods, this kind of subgrid scale methods. Finally, we look at the complete fluid structure interaction problem. In all the previous cases, you might have noticed that the moving bodies don't deform. They are rigid. They don't change the size or shape. Now come to the these problems where the structure may deform, like the one we had seen with the parachute. So here also the fluid flow around the structure may deform it due to pressure forces or shear forces, and then this deformation of structure may in effect change the volume of the fluid, the fluid domain. So it is a two-way coupling problem. There are different approaches to solve this kind of problem. Two approaches. One is called the monolithic approach. Second is called a staggered approach. Monolithic approach means both the fluid and the structural domain are solved using the same method. For example, I'll illustrate this with a conjugate heat transfer problem. Consider flow through a pipe. Flow of fluid through a pipe, and the pipe has an inner wall and an outer wall. So if the fluid is hotter than the pipe wall, there will be heat transfer from the fluids to the pipe, and then this heat from the inner heat flux to the inner wall will cause heat conduction through the wall to the outer wall, and from there to the ambient. To solve this problem, the flow field has to be solved by solving Navier-Stokes equation inside the pipe. Also, the heat energy equation has to be solved to obtain the temperature inside the pipe, inside of the fluid in the pipe. Then we need to calculate the heat transfer from the fluid to the pipe wall. And then in addition to that, the heat conduction in the pipe has to be calculated. So this can be done by using the same method. In monolithic approach, you can use finite volume method to solve the Navier-Stokes equation. And in the solid, all you have to do is suppress the fluid flow by setting, again, set porosity equal to 0, but solve only the heat conduction part of the energy equation. So in monolithic approach, the complete coupled problem is formulated using a single set of equations. So the same energy equation can be used to obtain the temperature both in the fluid and in the solid. In the fluid, it will consider all the convective terms. It will consider the convective terms, whereas in the convective terms and the conduction terms, and in the structure, it will consider only the heat conduction term. Then the second method is a partitioned approach or a staggered approach. In this, the flow field is obtained using one method, and the field in the structure, it could be a stress field, stress or strain of the structure, or the temperature in the structure obtained using is obtained using another method. For example, we use finite volume methods for flow field to solve the Navier-Stokes equation. So these and the finite element method in the structure. Finite element method to solve the energy equation and the deformation or stress field in the structure. The advantage of but in this case we are using two different methods in different fields. So these have to be coupled in some way. For example, for the flow solver, at the fluid structure interface, at the walls, for example, the structure velocity, we have seen the moving piston. So the flow should feel that movement of the structure. So the structure velocity and its position is an input now for the flow solver. What is the output from the flow solver? It is a fluid pressure and its velocity and its temperature. So the fluid pressure and velocity goes as an input to the stress solver as loads. The stress solver normally requires loads at the structural boundaries. So the fluid pressure and its velocity are used to calculate the loads on the structural boundaries. And if it is conjugate heat transfer problem, then temperature and heat flux from the fluid is used as a boundary condition for the stress solver. Now, once the structural analysis is done, the structure may deform. So the fluid domain is actually changing. So the fluid mesh has to be remeshed again. For that remeshing, the input is the structural position. So in general, we can say that in a partitioned approach, there is a flow solver, a structural solver, and a remeshing module. These are all coupled, and in the one time step, all of them should run. For example, the fluid flow, for example, in one approach, it could be the flow solver is invoked first. It is masked to solve the equations and get the solution in one time step, and the new fluid pressure and velocities are transferred to the structural solver, and it calculates the deformation of the structure, and that deformation of structure is used to remesh and change the fluid volume, and this loop goes on. Actually, this partitioned approach, there are two types of partitioned approach. One is called explicit. That means in one time step, we have already seen the concept of explicit and implicit when I talked about the Lagrangian particle tracking in the previous session. So you can go back, I mean, once I give you the material, you can go back to see that and the differences to see the explicit and implicit methods. So in explicit method, to advance or to do the calculations, we use all the boundary conditions and other things from the previous time step, or at the beginning of the time step. Whereas in the implicit method, we use the values at the end of the time step to update the properties. So in the explicit method, it's also called some sort of weak coupling. First, do the fluid flow simulations along with the moving grid. Then the transfer the forces to the structural solver, then compute the structural deformation, check whether the convergence is reached or required simulation time is over. Then they transfer the, if not, if yes, stop, otherwise transfer the displacement to the fluid, or go back to the beginning of the loop. The problem, this is good for problems with some of the problems, especially if the problem itself demands very low, very small time steps. We will see some examples of this. But normally, this is its accuracy is not very good. Its overall order of accuracy is, we have seen in the previous case, in the previous session, that of lowest order. We may have to use very small time steps. And also energy is may not be completely conserved. But advantage is that it is computationally less expensive. So an improvement upon this is a staggered approach with implicit method by multiple looping in the same time step. So we do one cycle, we check, get the solution. Then if that solution is not correct, repeat the same cycle using the new values or under relaxed values. For example, when we do the simulation, flow simulation or structural simulation, we get after structural simulation, structural displacement is obtained. But for the fluid flow in the next iteration, don't use the whole displacement for the previous positions, but instead somewhere in between, a weighted value of structural displacement it is equivalent of that semi-implicit method which we had seen, where we used the velocity at the middle of the time step to calculate the displacement, and we could get the accurate. You can see good description of this and merits and demerits in the thesis of Tremont. For example, in many cases, it was found that implicit method is essential. A strong coupling is essential to obtain the correct results. We can see the difference in the results between obtaining explicit and implicit. So in general, fluid structure interaction, fluid in our solve, we use a finite volume method to solve fluid flow equations, conservation equations for the fluid, and we use a finite element method for structural deformation and heat conduction in the structure, and their boundary conditions are exchanged. That is, structural deformation is used as a boundary condition for the fluid flow, and the fluid pressure and temperature and other properties are used as boundary conditions for structure at every time step. So one aspect in this is that we need to create two meshes, one for the fluid region, which you are already familiar with, and might have seen already, and another mesh, or we have to represent the structure also. For example, here you see the green region is a fluid region, and the red region is a structural region. So when we create the mesh or discretize that, there could be various scenarios depending on the difficulties in defining the problem. So this picture shows a discretization where the fluid mesh is exactly matching with the structural mesh. Okay, so the properties can be easily transferred from one to the other. But due to the complexity of problems, it is not sufficient. It may not be possible always to create such a mesh. So the solver and the coupling algorithms should consider or should be able to handle the non-matching mesh. For example, in this case, we can see the green region, the division of the green region. It is not exactly matching with the discretization of the structural, the red region, the structure. There is a mismatch. So the algorithms, and on the right hand side, you can see in like a cantilever, if it is bending, you can see that when the structure deforms, the fluid mesh also deforms appropriately. And there should be other features also to facilitate the modeling of complex problems. One of that is that suppose we want to model flow around a cylinder in a domain. So this picture shows flow past a circular cylinder. There is a cylinder here. So you see, cylinder is a very regular structure. So it is not always required to. Many times in structural analysis, this cylinder can be modeled using a 1D element. But the flow field should feel that cylinder. It should know that diameter, and it should see the effect of the cylinder. So in fluid, and we have these coupling facilities where the user can specify this 1D element for the structure and just specify the diameter of it, and it will automatically identify the fluid elements in the neighboring region and transfer the boundary conditions. Loads for the structural solver and the movements for the mesh movement, surface movements for the flow field. And the mesh there can be finer, see different problems may demand different fineness or levels of meshing. For example, a fluid flow problem may need only a coarse mesh, that is very large elements, but the structural problem may demand a finer mesh. So this picture shows an example where the coupling is done between a finer fluid mesh and finer structural mesh and coarser fluid mesh. So in general, multi-physics problems, so nowadays you take any engineering problem, it inherently involves a coupling of various physical processes. It involves fluid flow, it involves chemical reactions, it involves structural deformations, it involves electromagnetics, like in magnetohydrodynamics. It involves heat conduction. So in a general, an engineering problem involves all these processes. And so far, we used to isolate the problems and solve it as only one problem. But nowadays, the tools are being made available to handle the complex problems in a coupled manner. So if you look at the equations, governing equations, these are same as for fluid flow. These are same as equations shown in the previous sessions. But only difference now is that there should be some modifications to take into account the change in the control volumes. So I'll not go into the details of that. Otherwise, the equations remain same. Now let us look at the difference between the user will find when we solve a fluid flow problem and a fluid structure interaction problem. Sorry. In a normal fluid flow problem, first we prepare geometries using a CAD software. So in the present case, we need the geometries for both fluid and the structural domains. When we mesh, then these regions are meshed or discretized. So in this case, obviously, the fluid region has to be meshed and the structural region has to be meshed. But as I have shown you, if possible, you can have a non-matching mesh, but if not possible, you can also have a non-matching. So you can mesh them separately. There are a lot of freedom available nowadays. Then you can bring them together. And most of these identification of overlapping region is automatic. Then the next process normally is, after preparing the geometries and creating the mesh, you normally create the boundary surfaces and specify that the boundary conditions. So at that time, you may have to specify that this particular surface is a fluid structure interface. And also, the user may have to activate the remeshing capabilities. Why it is given as an option is that in many cases, even though there is a structural deformation, those structural deformations may be very small and it may not have any significant effect on the flow field. In that case, the problem can be solved by suppressing the remeshing. Still, we may get a good result. So there is an option to suppress or activate. So you may find these two additional things while applying the boundary conditions. The next step is assigning material. So in this case, materials are to be assigned both in the fluid domain and the structural domain. Properties they could be different because, as you know, the fluid is different from structure and its characteristics. So when we define the problem, then the next step, for the fluid flow, this moving mesh has to be activated in case there is a remeshing. and again that interaction between the fluid and structure. So and additionally, in addition to the flow and structure boundary conditions, there could be some remeshing parameters and conditions, because there are a lot of conditions available and we can control the regions of remeshing. We may not want to consider the remeshing to be done in certain regions, or it should be restricted to certain region for facilitating better convergence and so on. So those facilities are there. Then there are different numerical schemes for the coupling. For flow solver, there are schemes similar to that. We have already seen explicit coupling or implicit coupling, or in a time step you can do a fluid subcycling of structural solvers, because if it is too fast and so on. So various combinations are available and can be used. Just I'll demonstrate these processes using one simple example, that of a deflection of a cantilever plate in a rectangular channel. This is a rectangular channel. There is air flow from the left at a velocity of 37 meters per second. In the middle there is a structure, and it is fixed at the top, and it is free to bend in the direction of the flow. The right hand side picture shows its friend in the side. So this is a typical mesh. This is a mesh used for this problem. We can see that the structure is modeled using shell elements. Or is the fluid. That is another thing, that it is modeled as a shell element, but the fluid element on the left-hand side of the structure doesn't see the right-hand fluid element on the right-hand side. I mean, it doesn't transfer the pressure directly. That interaction has to come through the structural movement. And also, you can see that here the structural elements are triangular elements, and the fluid elements are hexahedrons. Then different boundary conditions are applied. The top flow is a no-slip valve for the fluid flow. The left surface is an inlet, and the right surface is an outlet. The bottom wall is also a no-slip valve. And for the structure, the nodes at the top are fixed, and other nodes are free to move. So this is the volume, zone 1. There are two zones now. Zone 1 is the volume containing the fluid. It contains air. The material assigned is air, and it has its own properties. And the zone 2 is the structural, is the structure comprised of structural elements. In this case, it is aluminium, and its properties are specified. We can see that when we do the simulation, the flow is from left to right. So it results in higher pressure on the left-hand side, and due to the flow's weight, there is lower pressure on the right-hand side. So the structure, there is a force on the structure from left to right, the positive x direction. So the structure deforms in the x direction, but it is fixed at the top. You can also see the pressure variations and velocity variations, velocity vector variations. We can see that fluid is accelerating below the structure because its area available is less. And on the mesh, once it reaches that steady state, you can see that it is also deformed. So this is a general procedure for fluid structure interaction. Problem involving in a deforming structure and changing flow field. Now we will see some real life case studies and introduce some of the phenomena involving fluid structure interactions. One of them is called aeroelasticity, which involves fluttering of the surfaces. For example, we say fluttering of flags, a flag, and there is a wind, it flutters. And many structures in engineering use does that. You can see the video of a plane and its wings. There is an airflow over the wing, and it exerts forces. We might have seen this if you sit near a wing, the window seat. You can observe this, and this is called flutter. And the wings or any other parts of the plane should be designed such that even in case of disturbance or onset of such movements, eventually it should be decreased and dampened such that then it is called a stable. But if any small disturbance causes amplification of this oscillation, it may lead to failure. In that case, it is called unstable. So whenever such these airplane wings or such structural components which are going to interact with the flow, they are designed, their stability is analyzed from the viewpoint of this. So here we need to model for airflow around the surface. So that is done by solving three-dimensional transform various toxic equations using CFD methods like finite volume methods. And you see that the structure deforms, that the structural deformation also is solved using appropriate method of your choice. And these are coupled by exchanging the forces on the structural surfaces and the surface movements. Another example of this, of the real life example, is the design of a chevron such that they are not susceptible to instabilities. If you look at Boeing 7, the twin liner planes, they use this kind of structure. You can see some peculiar shaped structures at the back of the engine. So these are, you can see they act like some sort of cantilever. They may flutter and it may break up, and these broken pieces may hit the plane when it is flying, and it can cause fire or explosion and other accidents. So in 2008, 2009, we have done this company which designs this kind of engines and manufactures this kind of engines. They did analysis of this using fluid NLP. So they found that their design was stable. So here you can see that the chevron oscillations, you can see the oscillations by the structure due to the airflow past it. The important point here is that this problem, the fluid flow itself is nonlinear. The structural deformation also can be nonlinear. So there are two nonlinear processes coupling with each other. It's very difficult to do analytical solutions in practical conditions. So more and more these kind of numerical tools are being used to study this. You can find more details about this case in the paper presented at NAFEMS. And NAFEMS is a good source for many articles on fluid structure interactions and in general for multiphysics simulation methods. So there are other problems involving fluid structure interactions. One of them is sloshing. So we have briefly mentioned about sloshing in the previous session with respect to that two-phase flow, the volume of fluid methods or free surface flows. So here you see that there is a cylindrical tank which contains a fluid, partially filled tank, and if it is subjected to an earthquake, the spectrum of earthquake is shown at the bottom, which gives the acceleration of the ground with the time. You can see it is very chaotic. When it is subjected to this kind, the tank on the ground also oscillates. So that will introduce a sloshing of the fluid, and that sloshing, with the sloshing, the fluid levels will be changing. So that will be changing the hydrostatic pressure forces on the structure. So that will cause a pressure imbalance there, and the structure may have relative deformations. So the similar technique can be used. We define, we create a mesh for the fluid flow domain and then for structural domain, and then indicate the fluid structure interface. And this animation shows a typical result obtained. Here, of course, the structural deformation is magnified by 100 times. Normally, the deformation of the structure will be millimeters. But you can see that this corresponds to the first cycle of the seismic oscillation. So you can see it comes to the left and then goes to the right. And you can see that even that movement causes different kinds of behavior at different places. Here, the boundary, the seismic movement, the movement due to earthquake are given as boundary conditions or accelerations to the nodes of the structure at the bottom. And that structural movement transfers the movement to the fluid and its interface also, which I had shown in one of the previous slides, that interface, the flow surface also oscillates. So another example of industrial application is the vibrations, vortex-induced vibration of heat exchange tubes. So this picture shows a heat exchanger across which there is a flue gas flow. It shows in another form. So you can see that the red lines shows the axis of the tubes, and the flow is around the tubes. The fluid domain is around the tubes. So this is the fluid mesh. The fluid mesh means the place where the fluid will be flowing. And the white color, that's the tube. And only the tube surface are modeled, but the tube is represented by the axis as a 1D elements. So you can see the different boundary condition here. At the inlet, there's a fluid flow coming in, the flue gas flowing in. On the right side, there is an outlet. And the structure is defined as a wall. So if you look at the pressure contour plot, you can see that at the inlet, pressure is high, and at the downstream, the pressure is low. Because of the tubes, there is a large pressure drop across the tubes. And we can also see there are weights and this vortex shedding behind the tubes and their interaction with the tubes in the downstream. And this shows an animation of this vortex shedding. You can see that there are oscillations in the flow field, and this will cause oscillating forces on the structure, which will result in the structural oscillation also. So it should be the gaps between the tubes or sufficient support should be given to the tubes such that these oscillations don't get amplified and destroy the system. This has been this kind of behavior has been observed in many actually industrial systems and caused failures. So nowadays, people use this kind of analysis to check the safety of such operational safety of such systems. So another example we have already seen in the introduction, the movement and deformation of the parachute. So the problem here in this scenario is that the deformation is quite large. Initially, there is not much fluid volume. It's almost closed. It's like an umbrella, and suddenly it opens. So from a small domain, the fluid mesh has to expand to the larger domain. There could also be openings in that. Then the whole thing may there could be translation, and also there could be rotation, and there is a strong effect on the flow field also. However, these kind of problems, here again we use a finite volume methods to solve the flow field and the finite element methods with the different features. Here you need to model the fiber, the cloth has to be modeled. At the same time, the ties are also should be modeled. So far, we consider the deformation of the structure, but there was no failure of the structure. But there are some scenarios or some situations when the structure may fail, and two different flow domains on either side of the structure may have to be connected. One example is the structural damage due to explosion. For example, in this case, this shows a room, and at the center there is an explosive, and there is a structure in front of that. Then there is the domain outside. So the explosion of that explosive, it will generate pressure waves as shown by the red region here. And this pressure wave will propagate through air and hit the structure. Once it hits the structure, so you can see that the structure will deform, and if deformation is too much, it may fail at different places. And after failing, that those regions will have to be opened, and the flow has to pass through those openings. So nowadays, methods are developed to generate such openings, looking at the local conditions of the structure, and activated. These elements are activated for the fluid flow. So at this point, I would like to mention also one thing, especially the problems involving explosion or detonation. You have to remember that the time scales involved are very, very small, a few milliseconds, or even less than that. If it is an explosion, it's a tens of milliseconds. Everything gets completed in less than a second. Nobody knows what has happened. If it's in case of a detonation, it takes even less time, maybe less than a millisecond. So we need a flow solver which can capture this transient, this unsteady variations in very small time scales. So normally we use it is called density-based methods, explicit solvers for the flow solver. So, and the structural deformation, it may be a bit slower than the fluid flow wave propagation. So you may be able to use a larger time steps for the structural deformation compared to the flow time steps. So in this case, we use normally when we couple this, we can use two different time steps. One smaller time steps for the fluid flow solver and a larger time step for the structural solver. So a segregated solver allows more freedom in choosing adjusting this kind of solution parameter, which will reduce the total computational time. This is another example of structural deformation due to explosion analyzed in a nuclear reactor. We will see more such examples tomorrow in the nuclear applications. Especially this kind of studies have become known and important after Fukushima accident 10 years back. This is another example of failure of reinforced slab when subjected to air pressure, explosion pressure. There is a slab at the bottom, and that gray color, and the top in the air there is small red sphere, which is higher pressure, and the pressure wave travels from there and hits the structure. And the structure deforms and fails. And here the damage at the bottom plate and at the top plate, they are compared with experimental data. So we can see that. Yes, sorry. Yes, Manish Singh, Mr. Manish Singh Bharati. Would you like to say something?
So you can go ahead. No one is
Okay. Yeah, anything? Is it? Should I change something or should I explain something more?
maybe it was an accidental switch on of mic or something.
Fine, fine. Or coding.